Welcome back. I want to go ahead and discuss the Lesson 3.1 notes, conditionals and counterexamples. A conditional is a statement that can be written in the form if P, then Q. An if-then statement is of the form if P, then Q, and we can use symbols to represent this. P arrow Q, read if P, then Q, or P implies Q. We say that the hypothesis of a conditional statement is the phrase immediately following the word if, which we will represent as P, and the conclusion of a conditional statement is the phrase immediately following the word then, which we will represent as the letter Q. So if we take a look at our model, P arrow Q or P implies Q, Q will be outside of this circle, or we can say that this circle P is inside of circle Q, and we will get into more information about that. Now let's examine the following conditional statement. Now a conditional statement, remember, is in the form if P then Q. So I have a statement right here. If I live in Austin, then I live in Texas. What I'm going to go ahead and do is identify the hypothesis and the conclusion. So I live in Austin is the hypothesis, in which I will underline once, because remember, the phrase immediately following the word if is the hypothesis. And the part that it says, I live in Texas, is our conclusion, because the phrase immediately following the word then is our conclusion. We can say that this is our P, and that will be our Q. Now I'm going to go ahead and take a look at this model over here, which I'm going to use this as a reference. So if this is Q, the bigger circle, then that means that this here is Texas. So this has to be P. P will be Austin. So we can relate this model to a real-life situation where we have the state of Texas, which contains all the cities. So this is going to have Austin, or you can put Dallas, or you could put San Antonio, etc., etc. Now we're going to go ahead and identify the hypothesis and conclusion of each conditional statement. We're going to underline the hypothesis once and the conclusion twice. Number one, if it's rainy outside, then I will bring an umbrella. So it's rainy outside is our P, and I will bring an umbrella is our Q. Number two, if today is Thursday, then tomorrow is Friday. Today is Thursday is P, which is our hypothesis, and tomorrow is Friday is our Q, the conclusion. Number three, if two lines form a right angle, then the lines are perpendicular. So two lines form a right angle is our P, and the lines are perpendicular, which will be our Q. Lastly, number four, an angle is a right angle if the measure is 90 degrees. So this is weird because the way it's written, the fact that our conclusion is the first part of the statement, which I will underline twice this time and call that Q, and then over here we have if the measure is 90. The measure is 90 will be our hypothesis, which we'll call P. And I will underline once. Some conditional statements are written without using the words if and then. To write these statements in conditional form, you first need to identify the hypothesis and conclusion. For the following statements, identify the hypothesis, underline once, and the conclusion, which we will underline twice. Then write the statement as an if-then conditional. So remember, it's going to be in the form if P, then Q. Number one, 16-year-olds are eligible to drive. So 16-year-old will be our hypothesis, P, and eligible to drive, which will be our Q. I can rewrite this as, if you are 16 years old, then you are eligible to drive. Number 2, the measure of an acute angle is between 0 and 90. Now, I just want to make sure that we understand this is actually the definition, so it can go either way. So I can write this statement as, number 1, if the measure of an angle is between 0 and 90 degrees, then it is acute. And for number 2, I can write the opposite direction, meaning I can say that if an angle is acute, then the measure is between 0 and 90 degrees. So what does this mean? This means the measure of an acute angle can be our hypothesis and conclusion, and the between 0 and 90 degrees part is also our hypothesis and conclusion, because this statement is a definition and it goes either way. Recall that we talked about conjectures in our first unit. A conjecture is a guess based on known information, but it has neither been verified nor shown to be false. We only need one false example called a counterexample to show that a conjecture isn't true. The counterexample could be a number, a drawing, or a statement. And I'm going to highlight this part because that's going to be important. So now what we're going to go ahead and do is show that each conjecture is false by finding a counterexample. Number 1, if x is an integer, then negative x is less than x. Now, whenever I'm looking at a conjecture, what I want to do first is look at the hypothesis. This is our hypothesis, in which I can assume true. Now, since x is an integer, our hypothesis, which we can assume true, well, that means x can only be an integer. It cannot be a fraction, or it can't be anything else except an integer. So what are integers, by the way? So if I give you a number line, well, integers contain negative numbers, 0, and positive numbers. So 0, 1, 2, 3 are integers, and we also need to include negative numbers. So negative 1, negative 2, and negative 3. And since this is a number line, it's going to keep on going forever and ever in both directions. So make sure that they are positive whole numbers, negative whole numbers, and 0. Those are integers. So what I like to do first is show that the statement is true. So suppose that x is equal to 1. 1 is an integer, right? Just like what we had over here. If x is equal to 1, then I'm going to look at the conclusion and replace both x's with 1. So I have negative x less than x. Then I'm going to replace both of these x's with 1. So I have negative 1 less than 1. Is negative 1 less than 1 true? Well, yes, that is indeed true. However, this conjecture is false because I'm going to prove with the counterexample. So let me go ahead and show you a false example. So what's an integer that will show this conjecture is false? Again, what do I need to do? We only need one false example called a counterexample to show that a conjecture isn't true. So let me go ahead and say that suppose that our integer this time is a negative number. Let x be negative 1. So again, my conclusion has negative x less than x. So I'm going to replace both x's with negative 1. So I have negative times negative 1 is less than negative 1. And negative times a negative is a positive. So positive 1 less than negative 1. Is positive 1 less than negative 1? No, positive 1 is greater than negative 1. So that means this conjecture is indeed false, which is what we want. So this means that x equals negative 1 is our specific counterexample, and that is how you do number 1. So what do I want you to get from this? Well, I need you to understand why we are doing these problems. This is basically logic. So if I'm looking at number 1 again, if x is an integer, then negative x is less than x. If x is an integer, is this always true? Well, no, it's not true, and that's why we're finding counterexamples to disprove that statement. And things are going to make more sense once I get into more examples. So let's take a look at number 2. If angle ABC is congruent to angle DBE, then angle ABC and angle DBE are vertical angles. So if angle ABC is congruent to angle DBE, then does it strictly mean that those two angles are congruent by vertical angles only? Well, let me go ahead and show you the true side of this statement. I'm going to draw two straight lines and form an X. Let's label this point A, let's call the vertex B, and then this point will be C, and then the right hand side of this picture, this point will be D, this is the vertex still, and this will be E. This is angle ABC, and this is angle DBE. And by vertical angles, those two angles are congruent. So I showed a true side of the statement. Now going back to the question that I asked earlier, if angle ABC is congruent to angle DBE, does it imply that those two angles are congruent by vertical angles always? Well, no, because I'm going to show you a counterexample with a picture. Now, I'm going to draw this, label this A, B, and E, and I'm going to draw some rays. So this point will be C, and this point will be D. So I have angle ABC, and this is angle DBE. And I'm going to say that angle ABC is congruent to angle DBE by drawing those arcs. So this shows that those two angles are congruent, not by vertical angles, just the fact that they are congruent. So this is my counterexample. So again, you're going to assume that the hypothesis is true and show that the conclusion is false by providing a counterexample. That's what I did for number 2. Moving on, number 3, for any x, x squared is greater than or equal to x. So let me go ahead and underline the hypothesis once and underline the conclusion twice. For any x will be our hypothesis, in which I will underline once, and x squared greater than or equal to x will be our conclusion, which I will underline twice. What do I need to do here? I'm going to show that the statement is true, and then I'm going to show that the statement is false by using a counterexample. Alright, well, the hypothesis says for any x, so I can use any number here. I can say, I'm going to show the true side over here. I can say that, let's use a whole number, a positive whole number. X is equal to 2. So if x is equal to 2, and my conclusion is x squared greater than or equal to x, I'm going to replace these two x's with the number 2. So I have 2 squared greater than or equal to 2. And 2 squared is just 4. 4 greater than or equal to 2. Is 4 greater than or equal to 2? Yes. So the example x equals 2 makes the conjecture true. But our goal here is to provide a counterexample which will make the conjecture false. So let's try x equals 0. So if my conclusion is x squared greater than or equal to x, let's go ahead and replace both x's with 0. So I have 0 squared greater than or equal to 0. 0 squared, 0 times 0 is just 0, which is greater than or equal to 0. Well, is 0 greater than or equal to 0? Yes. So that means that this example here makes the conjecture true, but that's not what we want. We need to find a counterexample which will make the conjecture false. Now, what if I tried a negative number? Well, let's say x is equal to -1. So my conclusion once again is x squared greater than or equal to x. So I'm going to replace these two x's with -1. So I'm going to have -1, the quantity squared greater than or equal to -1. Now, if you have something like this and you're replacing x with -1, you need to make sure you put the parentheses whenever you're replacing. I didn't have to put parentheses for that x because it wouldn't change anything. But in this case, it will. And you're going to have to believe me on this one. Okay, so again, when you have something like x squared, replace the x with -1, but remember to put parentheses around the -1. Okay, so -1, the quantity squared, -1, the quantity squared is like saying -1 times -1. And a negative times a negative is positive, so -1 times -1 is +1. So this is going to be 1 is greater than or equal to -1. And is that true? Yes, it is indeed true. 1 is indeed greater than -1. So this example here will make the conjecture true. But again, I need to find that counterexample. So I tried a positive number, I tried a negative number, and I also tried 0, but none of these examples work. So what do I need to do? Well, I need to read the statement or the conjecture again. It says for any x, x squared is greater than or equal to x. Well, x can be any number. It can be a positive number, it can be a negative number, it can be 0, it can be a decimal, it can be a fraction. But, we didn't even try decimal or fraction, so let's go ahead and try fraction. So let's say that x is equal to 1/2. That's going to be my example, my attempt trying to provide a counterexample. So here we go. X squared greater than or equal to x. Let's go ahead and replace these two x's with 1/2. So I have 1/2 raised to the second power. So put the parentheses around the 1/2, which is greater than or equal to 1/2. Okay, so 1/2, the quantity squared is basically saying 1/2 times 1/2. So 1/2 times 1/2, well, 1 times 1 is just 1, and 2 times 2 is 4. So 1/2, the quantity squared, is 1/4. Is 1/4 greater than or equal to 1/2? Well, let me go ahead and draw a picture. So here's a circle with some slices, and this is a picture showing 1/4 of a pizza. And then over here, this is 1/2. So which one's greater, 1/4 or 1/2? Well, it's going to be 1/2. 1/2 is greater than 1/4. 1/4 is not greater than or equal to 1/2. So this is a counterexample. So I can safely say that this is false and 1/2 is my counterexample. That's how specific my counterexample is. Now let's take a look at the bottom part of today's notes. A conditional statement has a truth value of either true or false. It is only false when the hypothesis is true and the conclusion is false. And I can rephrase this as, if the hypothesis is true and the conclusion is false, then the conditional statement, whatever that is false. To show that a conditional statement is false, you need to find only one counterexample where the hypothesis is true and the conclusion is false. Determine if each conditional statement is true. If false, give a counterexample. Number 1. If you live in Terlingua, then you live in Texas. What I'm going to go ahead and do is I'm going to underline the hypothesis once and the conclusion twice. You live in Terlingua will be underlined once because that's our hypothesis. You live in Texas is our conclusion, so therefore I can underline that twice. Now let's take a look at the hypothesis here. You live in Terlingua. Well, is there a place called Terlingua anywhere in the world? If you Google it, yes, there is a place called Terlingua. So I'm going to go ahead and say true for the hypothesis here. Now, if you live in Terlingua, does it imply that you live in Texas? Yes, Terlingua is a place in Texas. So I can go ahead and say that the conclusion is also true. Now, since I have both trues here, well, what can I say about this whole conditional statement here? Well, the conditional statement itself, since I have both trues here, is true. So please remember what I highlighted over here. It is only false when the hypothesis is true and the conclusion is false, it being the conditional statement itself. Number 2. If an angle is obtuse, then it has a measure of 100 degrees. An angle is obtuse is our hypothesis, which I will underline once. It has a measure of 100 degrees is our hypothesis, which I will underline twice. Now let's take a look at the hypothesis here. An angle is obtuse. Can an angle be obtuse? Yes. So I can go ahead and say that the hypothesis is true. Now, if an angle is obtuse, does it imply that it strictly has a measure of 100 degrees? No. So I'm going to go ahead and say false, and I'm going to provide a counterexample. Now, remember, if an angle is obtuse, it has an angle that is greater than 90 degrees, but less than 180. So I can provide a counterexample and say that the angle could be 160 degrees or 170 degrees, etc., etc. Look at my counterexamples. These are specific counterexamples to disprove the conditional statement. So, since I have a true and a false, then I can go ahead and say that the conditional statement is false because the hypothesis is true and the conclusion is false. Number 3, if an odd number is divisible by 2, then 8 is a perfect square. So, an odd number is divisible by 2. That's my hypothesis, which I will underline once. 8 is a perfect square, which is my conclusion. Now, before I delve into number 3, let me go ahead and briefly explain what a perfect square is. A perfect square is essentially where you have an integer multiplied by itself. For instance, 4 is a perfect square because you have 2 times 2. 2 is an integer, and it's being multiplied by itself, so you get 4, where 4 is the perfect square. So let me go ahead and show you a picture. I have a 2 by 2. So 2 times 2 is going to be 4. So 4 makes this perfect square. But if I have a 2 by 3, then you're going to have a rectangle. Now let's go ahead and go back to number 3. If an odd number is divisible by 2, then 8 is a perfect square. Well, can an odd number be divisible by 2? No, I don't think there is an odd number to be exact, can be divisible by 2. So I'm going to go ahead and say false for this hypothesis here. Well, does it imply that 8 is a perfect square? Well, 8 is not a perfect square because there is no integer multiplied by itself that'll give me 8. So I can go ahead and say false for my conclusion here. Okay, and I can go ahead and draw my 2 by 4 here. And as you can see, that's a rectangle. So, if the hypothesis is false and the conclusion is false, what does that make the conditional itself? Is the conditional true or is the conditional false? Now, if you think that the conditional itself is false because you see a false hypothesis and a false conclusion, I totally understand, but we gotta recall what it says over here. It is only false when the hypothesis is true and the conclusion is false. That's the condition here. If this was true and this was false, then we can say that the conditional itself is false. But both of these truth values are false, so the conditional is true by default.